Yeah, you know it's practice exam 3S. Okay, in this first question, we're trying to find the pH of a 0.72 molar solution of HClO3. So the first thing we want to do is ask ourselves, what is HClO3? How will we identify this? Well, this is a strong acid. What do we know about strong things? Do they dissociate a little bit? Nay, a whole lot of it. So in a solution of HClO3, we're going to use a full-headed arrow to describe its dissociation into H plus and chlorate, ClO3 minus. So strong acids are actually pretty straightforward to calculate the pH of, because for every 1 mole of this we're going to get 1 mole of H plus. Likewise, for every 1 molar of HClO3 we're going to get 1 molar of H plus. So what I like to do for any strong acid except for sulfuric acid, H2SO4, is whenever I see a solution of this, we don't care what this negligible anion is. We care about the H plus. And our concentration is just going to be equal to the initial concentration of the strong acid that we had. So to find the pH then, all we have to do is take the negative log of that 0.72, and that will give us our answer of pH equals 0.14. Choice A. In this question, we're looking at 4 different carboxylic acids. And for our purposes, the idea what the carboxylic acid is. So these are good acids for multiple reasons. First of all, you have this oxygen here, which creates a dipole moment. You also have this oxygen-hydrogen bond over here, which has a polarized bond. Remember, the more polarized we can make that OH bond, the stronger the acid will become. So now the question becomes, how can we make this acid even stronger? What can we add in to help polarize this bond further? So having this polar bond up here actually has a downstream effect on this bond and pulls electron density further away from the hydrogen. And remember, the H plus is attracted to the negatively charged electrons. So the further we can pull these electrons away, the electron density, the less attracted it will be, the weaker the bond, the easier it will be to dissociate, and the stronger the acid will become. So we can make a stronger acid by adding in more electronegative atoms. So like, for example, if we add in a few chlorines, well, this is going to have a downstream inductive effect on this bond over here and will actually create an even more pronounced, let's just erase this, an even more pronounced polarized bond, which will pull these electrons even further away from that hydrogen. So it'll make a more polarized bond, which is easier to break, which makes a stronger acid. So long story long, when ranking carboxylic acids, the more electronegative atoms that we have in our carboxylic acid, the stronger it's going to become. So the weakest one is going to be the one that only has this 1 bromine here. Next is going to be, well, we've got 2 bromines on this one, so 3 is going to be next. After that, notice how on acid 2 we've got 2 bromines and a chlorine. So that's going to be our next in terms of acidity. And then finally, the most acidic of them all will be this trichloroacetic acid with 3 chlorines. So the order is 1, 3, 2, then 4, which is choice D. Okay. In this problem, we're trying to find the pH again, and really finding the pH of any solution comes down to identification. So here we have calcium hydroxide, which we would identify as a strong base. So when strong bases dissociate, do they dissociate a little bit? Well, what the answer with strong things is no, not a little bit, a whole lot of it. So dissociate into calcium 2 plus, this cation, and 2 hydroxides, 2 OH minuses. Now then, the important thing to note, it's always important to write these reactions because notice that for every 1 calcium hydroxide, we're actually getting 2 hydroxides. So what that means is we're going to need to take that into account, the stoichiometry here. So we've got 2.5 times 10 to the negative 5th molar calcium hydroxide. And then we're going to do a little dimensional analysis here. For every 1 molar of calcium hydroxide, remember we're going to end up with 2 molar hydroxide because of that 1 to 2 ratio. But then, after we do this, molar of calcium hydroxide will cancel out, and we're left with 5 times 10 to the negative 5th molar hydroxide. Now, all we have to do is take the negative log of that, which will give us the POH. So the POH will be equal to the negative log of the hydroxide concentration, 5 times 10 to the negative 5th, which ends up being POH equals 4.3. Now, what are we looking for in this problem? We're actually looking for pH. So just remember that at 25 degrees Celsius, pH plus POH equals 14. So we'll subtract the 4.3 from 14, which will give us our answer of 9.7. Okay, in this problem, we're asked to identify the acid and conjugate acid, and we're given a pro tip here. Label each chemical species. So we want to see where a proton is transferred from and to. So notice that this hydrogen here, this proton, goes from chemical species 2, and it ends up going on to this phenol right here. So what we're going to do is, whatever loses the proton, that is the acid, and whatever gains the proton, that is the base. Okay, so then, whatever starts off as our acid, once it loses its proton, it becomes the conjugate base. So this is our conjugate base right here. And likewise, the base, once it gains a proton, becomes the conjugate acid. So the acid is chemical species 2, the conjugate acid is chemical species 3. This question is a hashtag identification station. We want to know which of these are strong acids, so let's go through. HF, not a strong acid. You know what? In fact, let's just list the strong acids. There are HCl, HBr, and the friendliest acid of them all, HI, hydriodiodic. Okay, in the words of great poet, philosopher, and musician John Bon Jovi, whoa, we're 3/7 of the way there, which is pretty close to halfway. The other 4 are oxyacids. There are HClO3, HClO4, so chloric and perchloric acid, nitric, HNO3, and sulfuric, H2SO4. So make sure that you know these strong acids. And if we do, it makes this problem really, really easy. Ding, ding. So 3 and 4 for the win. This question is asking about the relative strength of HCl and HI. Now, we'd classified both of these as strong acids. So for our purposes, these dissociate completely in aqueous solution. But if you're an organic chemist, there actually is an importance between which strong acids are stronger acids. So to analyze this, let's consider the structures of HCl. Cl is a relatively small atom. It's in group 3. And then we have HI. Iodine is a much larger atom. It's in group 5. So it's a lot further down, which means this is a much longer bond. Now, if we compare these two, longer bonds are substantially easier to break, which means HI is going to be the strong acid here. Again, if we were looking for pH in an aqueous solution, we would consider them to both dissociate completely, but it turns out that HI is actually about, I think, 1,000 times stronger or so. And the reason is for this longer bond length. So the answer is choice D. HI is the stronger acid because of its bond length. All right. In this question, we're looking to compare the acidity or basicity of a whole bunch of different compounds. Now, notice all of these are neutral compounds that all have oxygen and one other element in them. So these are actually just known as oxides. And there is a nice rule that we can use for oxides based off of periodic trends. So I'm going to draw, or attempt to draw. Well, it's looking okay. A little got a little worse. Oh well. Periodic table of the elements here. Oh, there it is. And our trend for oxides and acidity is as our elements become more and more non-metallic in character, the acidity of the oxides increases. So basically, as we go up and to the right, we end up getting our more acidic oxides. So let's compare these different ones that we have in this particular problem. And just note, if we were asked to classify these rather than just compare their acidity. A good general rule of thumb, and here's the stair step. This isn't to scale my periodic table here, but a good general rule of thumb is that the metal oxides are basic, the non-metal oxides are acidic, and then the far transition metal ones, the ones that are far to the right of the D group, and are metalloids. These ones aren't going to be really acidic nor basic. They're actually going to be amphoteric. So this would be the way that we would classify them just generally, but here we want to actually put these in order. So let's see where these different elements are located on the periodic table and use our trend to do so. So rubidium is a group 1 metal. It can be found here on the periodic table. This is going to be a basic oxide. Up next we have nitrogen. So nitrogen can be found right in here. So it's going to be an acidic oxide. Up next we have carbon. So carbon is found right next to nitrogen. And then finally we have silicon. Silicon is a metalloid. We can find it right here. Okay, so if we're to arrange these in order, again, as it goes up and to the right, they become more and more acidic. So the most basic is going to be the RbO2, rubidium oxide, followed by silicon's oxide, aka silicon dioxide, which is what you can find in sand. And then after that, we're going to end up having carbon's oxide, which is carbon dioxide. This is actually if you pump carbon dioxide into water and you make fizzy water, this is what makes it acidic, is that it ends up forming carbonic acid. And then finally we have nitrogen's oxide, aka N2O3. And in case you're wondering, this actually turns into nitric acid, HNO3, in water. So this is our order. And our answer then is going to be none other than choice B. This wants to know which of these anions is not a negligible base in aqueous solution. Okay, so let's consider what happens with strong acids, and let's use classic HCl. So strong things, what makes them strong? It's the fact that they dissociate completely. We use a full-headed arrow. Turn into, in this case, H+, and the conjugate, quote-unquote, base, Cl-. Okay, so notice here that this is a full-headed arrow. This is a one-way street. HCl will break apart into H+ and Cl- in aqueous solution, but these things do not have a way of going back. So Cl- can't even grab onto a proton that's floating around freely in aqueous solution. Is there any way that's going to be able to hydrolyze water? Yeah, no, not so much. So I like to call this the Taylor-Swift hypothesis with regards to strong acid dissociation, because the H+, well, it's basically saying, we are never, ever, ever getting back together. And the Cl- responds by informing the H+ that it has an indie record that's much cooler than H+'s. Anyway, long story kind of goofily put here. Strong acids dissociate completely into negligible bases. So, between these, we're looking for which one is not the conjugate of a strong acid. So, nope. There we go. For our purposes, anything with a negative charge that's not the conjugate base of a strong acid can act as a base in aqueous solution. Alrighty, in this problem, we're looking at a solution of sodium cyanide, NaCN. One of the things that I like to do when doing an acid-base problem is, so if we classify NaCN, it is a salt, right? So for our acid-base unit, really any salt that we look at is going to dissociate completely. This will turn into Na+, and cyanide, Cn-. Okay, then we want to ask ourselves, would this be acidic, basic, or neutral? So Na+ is a group 1 metal cation. All group 1 metal cations are negligible in aqueous solution. Cn-, notice it has the negative charge here, and it's not the conjugate base of a strong acid. So anything other than Cl-, Br-, I-, ClO3-, ClO4-, NO3-, and HSO4- can act as a base in aqueous solution. So this is going to be a weak base. Okay, so we're trying to find the pH of a weak base solution. All right, now something I want to point out, something else I'd like to do is we're given a Ka of HCN here, and I like to ask myself, is the thing that we're given a K value for, in this case HCN, the same chemical species as what we're given in the problem stem? Are these the same? Nah, they're very similar, right? So the relationship here is that CN minus is the conjugate base of HCN. Okay, so now for any weak base, what we're going to do is we have to react it with water to find the pH. So it's going to be CN minus plus H2O, because H2O is going to be the source of our hydroxides here. It's going to be an equilibrium reaction, and our CN minus is going to grab a proton to form HCN, and we're going to form hydroxide here. Okay, so for any solution of weak acid or weak base, when in doubt, ice it out. I'm going to do an ICE table here. Classic. And in this problem, we're told that we're starting with a 2 times 10 to the negative fourth molar solution of NaCN. It's another way of saying, since it's a 1-to-1 ratio, that it's a 2 times 10 to the negative fourth molar solution of CN minus. So this is going to be 2 times 10 to the negative fourth molar. Water? We don't care. We love it. Unless told otherwise. 0 for these. Okay, so our change is going to be minus x, and then over here in product land, plus x and plus x. 0 plus x is x, 0 plus x is x, and 2 times 10 to the negative fourth minus x is 2 times 10 to the negative fourth minus x. Cool. Okay, now we have half the problem done. We need to combine this with our equilibrium expression for great results. So our equilibrium expression is just going to be, now this is a base hydrolysis, right? We're taking water and we're turning it into hydroxide. So is this going to be a Ka reaction? Nay, it's a Kb. So we'll plug in, it's going to be HCN times OH minus, all divided by our CN minus. So products over reactants is pretty classic. Plug in our values here. But wait, oh no, we're only given the Ka of hydrocyanic acid. Whatever shall we do? Is there a relationship that we can utilize? Well, you bet there is. Because for any given conjugate acid-base pair, Ka of the acid times the Kb of the base is going to be equal to our constant Kw. So we're going to solve for this. We're given our Ka here. The Ka is 6.2 times 10 to the negative 10th. That times Kb, which is what we're solving for here, is going to be equal to Kw, which at 25 degrees Celsius is 1 times 10 to the negative 14th. So when we solve for Kb, we'll get 1.61 times 10 to the negative 5th. So let's plug that into our equilibrium expression. 1.61 times 10 to the negative 5th is our Kb, and that's equal to x times x, which is x squared, over our, remember, because our k is on order of 10 to the negative 5th or less, we can assume that this x here is negligible compared to the initial amount that we started with. So we're just going to plug in 2 times 10 to the negative 4th right here. Okay, so then what we're going to do to solve for x is multiply both sides by 2 times 10 to the negative 4th, and then take the square root. And when it's all said and done, we'll end up getting that x is equal to 3.2 times 10 to the negative 9th. All right, and then just remember, that represents the concentration of hydroxide. So if we take the negative log of that, we're getting the POH. Excuse me, I made an oopsie doopsie, so this is not accurate. Let me just go back a step. X squared is equal to 3.2 times 10 to the negative 9th. So we'll have to take the square root of both sides, and that will give us our actual value of x, which is 5.67 times 10 to the negative 5th. So if we take the negative log of that, that will give us our POH, which is equal to 4.25. So the POH is actually 4.25, which means we can subtract that value from 14 to get our pH. And the pH is going to equal then, when we do that, 9.75 for the win. Okay, this question wants us to identify which of these salts will have a neutral pH at 25 degrees Celsius. So, in identification, what we basically want to do, is write out our dissociation. So, LiBr, for example, would dissociate into the lithium cation and the bromide anion. And generally speaking, a good rule of thumb we want to ask ourselves is the cation acidic and is the anion basic? Now note there are some acidic anions like HSO4-, for example, and there are some anions that can act as both acids and bases, so like the conjugate bases of polyprotic weak acids are amphoteric. But generally speaking, when classifying salts, good rule of thumb is ask yourself, is the cation acidic? Because things with positive charges have a better chance of being acids attracting in electron density. And then ask yourself, is the anion basic? And this generally will work for most salt identification problems because things with negative charge density tend to be better at donating negative charge density. So Br- is the what of a what, therefore making it what? It's the conjugate base, you can't see it, but I'm air quoting right now, of a strong acid, therefore making it negligible. Li plus is a group 1 metal cation, which makes it also negligible. So we actually already have our answer here. For posterity's sake, I'm going to show what the other ones would be. So iron chloride would dissociate into Fe3 plus and 3 chlorides. I'm going to show the dissociations first, and then we'll identify each one. Calcium chlorite would turn into calcium and chlorite. NH4, ammonium chloride, would turn into NH4 plus and Cl minus. And then finally, NaNO2 would turn into Na plus and nitrite NO2 minus. So if we go through and identify these, Cl minus is negligible, Ca2 plus negligible, Cl minus negligible, and Na plus is negligible. So to classify the rest of these, iron 3 plus, any transition metal cation is going to be acidic. Chlorite, ClO2 minus, this is going to be basic. NH4 plus, all ammonium salts are acidic. And then finally, nitrite, NO2 minus, is going to be basic. So the only one here that is neutral is going to be our LiBr.
Rick T. Cat uses aniline to help him produce synthetic rubbers for his car. He drives a nice car. What is the pH of a 0.55 molar solution of aniline if it has a Kb of 4.07 times 10 to the negative 10th at 25 degrees Celsius? So first and foremost, we need to decide whether this is going to be a basic or an acidic solution. And we have two hints to help us figure this out. One is the fact that aniline has this free amine group here, NH2, and that will only have 3 bonded atoms to it, and it will have 1 lone pair. So aniline is going to be basic. And we can confirm this also by seeing that they gave us a Kb. So it must be a base. Okay, so now we can go ahead and rule out a few options because we know that our pH should end up being greater than 7. So boom, we're already rid of answers A and D. Now let's go ahead and write the reaction. We have our aniline base. And whenever we're writing a base hydrolysis reaction, we need to include water, which is a liquid. And we will then have the protonated conjugate acid of the aniline, which will have a positive charge and leave behind hydroxide. And so our goal for this is to eventually figure out the concentration of hydroxide, because once we do that, we can figure out the concentration of protons and therefore our pH. And so to do that, we're going to need to use an ice table with our initial amount of aniline of the 0.55 molar. We always use molarity in ice tables. We're not going to bother with water since it won't be in our equilibrium expression as a liquid. And they didn't tell us anything about these, so we'll give them an initial of 0. We'll subtract from the side we have stuff from, and we'll add to the side where we don't have anything. Okay. And so now we have our equilibrium expression for each individual component. We need to put those together into a KEQ, in this case KB expression, which will be equal to our concentration of products to their power of their exponents divided by concentration of reactants to the power of their exponents. We'll have C6H5 NH3 plus times hydroxide, all divided by the concentration of our original aniline. And this will be equal to that Kb value of 4.07 times 10 to the minus 10. Now this value is really small. It's a really small K, which tells me that we can go ahead and ignore any added or subtracted x's. So we can ignore the x associated with the aniline, which helps us to simplify our expression to x squared divided by 0.55. So now we can multiply our Kb by the 0.55, and then take the square root of that value to see that our x is equal to 1.5 times 10 to the negative 5th molar. But then we have to remember what that concentration is corresponding to, and that is corresponding to hydroxide, or to the conjugate acid. And so when we go ahead and take the negative log of this number, what we end up with is a POH of 4.83. And so then to find pH, we'll just do 14 because we're at 25 degrees Celsius minus 4.83. And we can see then that our pH is 9.17, which is indeed above 7, which was our initial prediction. So our final result makes sense.
Hydroxylamine, so really quickly, keyword here being amine, so a hydroxyl group is an OH. I'm just going to draw the Lewis structure here, sort of give us a way of thinking about this. So this is our Lewis structure, and for our purposes, any neutrally charged amine is going to be able to act as a base in aqueous solution. Now, some other ways that we can find out that it's a base is, notice that we're given a pKb in this problem. And our goal is to find the pH of a 0.25 molar solution of hydroxylamine at 25 degrees Celsius. So, pKb, what does that mean? Well, remember, P always means the same thing. It always means the negative log base 10 of, in this case, since it's pKb, this would be of Kb. And we know that that's 7.97. So if you know the pKb, you can find the Kb, which is going to allow us to solve this problem. So multiply both sides by -1. We'll get the log of Kb is equal to negative 7.97. And we'll do 10 to both powers. And that will give us our Kb, which is equal. 1.07 times 10 to the negative 8th. Cool. Now, with everything we need to complete this problem. So anytime we have a weak base and we want to find the pH of the solution, when in doubt, ice it out. And our reaction is always going to be for base hydrolysis, whatever our base is, in this case, hydroxylamine, plus water. We're always going to react our weak bases with water. If we're just looking at a solution of weak base, yields the conjugate acid and hydroxide. All right, so now let's do our ICE table and plug in the values that we're given. So we're told in this problem that we have a 0.25 molar solution. Cool. So 0.25 molar. We don't care, we love it. 0 and 0. The change is going to be minus x plus x plus x. And we're going to end up with 0.25 minus x. 0 plus x is x, and 0 plus x is x. Cool. Now we need to plug everything into our equilibrium expression. So Kb is equal to products. So we have the HONH3 plus and hydroxide, all divided by the concentration of reactants, HONH2. Once again, since we have a K that is on order of 10 to the negative 5th or less, we can assume that this change is negligible compared to the initial amount of 0.25. However, it will be significant compared to the 0 that we start with for the products. So let's plug in our values. 1.07 times 10 to the negative 8th is equal to x times x, which is x squared, over 0.25. So multiply the 0.25 through and take the square root of both sides to solve for x. We'll end up getting x is equal to 5.18 times 10 to the negative 5th. Okay, so if we take the negative log of that, that will give us our POH. So the negative log of that ends up equaling 4.29. Subtract that from 14 to get our pH at 25 degrees Celsius, which would be 9.71. All right, here we are analyzing a titration curve. And we're titrating a weak acid with a strong base. And there's a few different ways that we could tell this. First of all, we're told it in the question stem that's a weak acid with a strong base. But if we weren't told that, we could look for one key part of this particular graph. Now, there's going to be two parts that you're going to want to be able to identify, and I'm just going to point both of them out. So, first of all, if we look for, at some point, all titration curves will encounter a rapid spike or plummet in the pH. So if you look at the halfway point of that spike or plummet, this is something called the equivalence point. If we look at the pH at the equivalence point, we can tell what we're looking at. So this is, let's see here, at our equivalence point, it looks like that's about a little bit over 8 is our pH. So this shows us that this must be a weak acid being titrated with a strong base. Now the other part, the part that's going to be more useful for our purposes in this problem is, once you've identified the equivalence point, it looks to be at about 15 milliliters. If you cut that volume in half, you find what's called the half equivalence point. The other way that you can find the half equivalence point is, this region here is our buffer zone, where the pH is not changing that appreciably. If you look for the halfway point in the buffer zone, that will be our half equivalence point. So our half equivalence point, it looks to be about here or so. Not there. It's to be about here or so. Indeed, that's about half the volume to reach the equivalence point. And the reason why this point is significant, so at the half equivalence point, the pH of the solution is equal to the pKa of whatever acid we're using. So if we I meant to use the line feature here, 1 second. So if we look at this, it looks like the pH at the half equivalence point is about 3.3 or so. So that means, since pH equals pKa, we can say the rough approximation of our pKa is about 3.3. Remember, p means the negative log of Ka, so if you know the pKa, you can find the Ka. So I'm going to multiply those by -1. I'll get the log of Ka is equal to -3.3. Then do 10 to both powers, and we'll end up getting that the Ka of this weak acid is about equal to 5 times 10 to the -4th. So you might get a little bit of leeway in your answer based off of how precise your identification of the pH was. Notice that none of the answers are on remotely close to the same order of magnitude. So even if your answer is a little bit different here, as long as you're looking at the right order of magnitude, you're good to go. So again, your number may vary a little bit, but there should be only one answer that's remotely close to whatever you got. Okay, in this problem, we're looking at benzoic acid. And we're not given explicitly the formula, but we're given a skeletal structure. So benzoic acid is C6H5COOH. It is a carboxylic acid. But pro tip, if you're given a skeletal structure of a weak acid and you don't feel like counting up the carbons and hydrogens, you can really just simplify your life by calling it HA. Ha! It's the funniest generic weak acid, because we know all weak acids do the same thing in aqueous solution. They dissociate in an equilibrium reaction to form H plus and the conjugate base. So anytime we want to know how much of a weak acid is going to dissociate, when in doubt, ice it out. And we're starting with 1.25 molar of the Ha, 0 of the H plus, and 0 of the A minus. Our change is going to be minus X plus X and plus X to leave us with X and X for our two products, and 1.25 minus X for our reactant. All right. So now, if we want to find out what X is, because here we're looking for percent ionization, we want to know how much of our Ha is dissociating, what fraction of it is, well, what percentage of it is. So we need to write out our equilibrium expression. That expression is products over reactants, classic, H plus times A minus all over HA. So now we'll plug in our values and solve. Let's see what we end up getting. So we have our I wrote KB. This is a Ka reaction. Here we go. We have our Ka, 6.46 times 10 to the -5th. And that's equal to X times X, aka X squared, divided by, and just like every other weak acid and weak base that we look at in this unit, we can assume that X is negligible compared to the initial 1.25 that we had. And just to verify that, we can see that this is on the order of 10 to the -5th. So I'm just going to plug in the 1.25, and then we're going to multiply the 1.25 through and take the square root of both sides to get X, and we'll end up getting 8.97 times 10 to the -3rd. So now the question is asking for what is the percent ionization. And rather than memorize a formula, I like to think about what percent ionization actually means. It literally means what percent of our initial acid is breaking apart to turn into our hydronium, or the conjugate base, since they're both equal to X. So the formula is going to be percent ionization is equal to whatever H plus concentration ends up being, or A minus, doesn't matter, divided by the initial amount of the weak acid that we had, times 100. So let's plug in some values and see what we get. Our concentration is 8.97 times 10 to the -3rd, and we start off with 1.25 molar. So all this times 100 will get us our answer of 0.7 0.19%. In this problem, we have a titration. Ooh. And what we're adding is NaOH, which is a strong base, to a solution of CH3COOH, acetic acid, which is a weak acid. So the heart of any titration is the reaction. So we have our acid, CH3COOH, and it doesn't matter if we add in NaOH or KOH or LiOH. It's just a source of hydroxide, so it's going to be OH minus. And whenever we have a titration, I'm going to use an equilibrium arrow? Nay, we're going to use a full-headed arrow, because this is going to keep reacting until the limiting reagent is used up. So the OH minus is going to deprotonate the acetic acid to form acetate, CH3COO minus, and water. So for any titration, when in doubt, is it out. I'm going to do an ICF table here. Remember, ICF tables use moles. So we need to use the relationship that moles are equal to molarity times volume in liters. So using this information for our acetic acid, it is 4 molar times 0.2 liters, which ends up giving us 0.8 mole of acetic acid. We can do the same thing with the hydroxide. The hydroxide is 2 molar and 0.05 liters, which will give us 0.1 mole of this. We're starting off with 0 acetate, and for water, well, classic, we don't care, we love it. Now, let's fill out our ICF table. Our limiting reagent is the hydroxide, so it's going to be minus 0.1, minus 0.1, and in products land, plus 0.1, to leave us with 0.7, 0, and 0.1. Wait a minute. Hold the phone. We have a conjugate weak acid, weak base pair together in appreciable concentrations in the solution. Oh my goodness, what are we dealing with? That's right, we're dealing with a buffer solution. A buffer solution. So we can just use Henderson-Hasselbalch now to finish this problem. And as a reminder, Henderson-Hasselbalch is pH is equal to the pKa plus the log of the ratio of base to acid. And the ratio here can be in terms of moles, millimoles, molar, millimolar. Doesn't matter as long as our units are consistent. So we can just plug in the moles that we get. So the pH of this buffer solution is going to equal, pKa just means the negative log of the Ka, which we're told is 1.8 times 10 to negative 5th, plus the log of base. The base is the 0.1 mole over the acid, which is 0.7 mole. So let's see what we end up getting. pH is equal to, the pKa is 4.74 for acetic acid, plus negative 0.85, which gives us our answer of the pH is equal to 3.89. This question asks us, what is the reaction that corresponds to the Ka3 of H3PO4? And honestly, I would write out each dissociation here because might as well be careful and make sure that we get the right answer. So Ka1 is going to be the fully protonated acid dissociating into H plus and H2PO4 minus. And I recommend writing in the state of matter here. Okay. Note, I'm not doing that here just because I'm running on a tablet, taking more time, but these are all aqueous species. All right, so Ka2, we're basically taking the first conjugate base, and we're dissociating that further because it has 2 more protons it can lose. So it's turning into H plus and HPO4 2 minus, where each Ka is a loss of a subsequent proton, which leaves us with Ka3, which is what we're looking for, which is HPO4 2 minus, losing a proton to become H plus and phosphate, PO4 3 minus. So which reaction corresponds to that? Well, it is this one here, reaction B. All right, in this question, we're asked about a titration into a buffer. And our buffer consists of dihydrogen sulfide, H2S, and we've got this NaHS. This is a salt. The Na doesn't contribute to the pH, it's just HS minus in disguise. So we have this conjugate weak acid, weak base pair. And the question is, what will happen if we add in a strong base? So if we're adding in a strong base, it doesn't matter if we add in NaOH or KOH or LiOH, it's just a source of hydroxide. So which of these will hydroxide preferentially react with? Will it react with the weak acid component or the weak base component? Hydroxide would react with the acid component, right? So it's going to be plus OH minus. Again, it doesn't matter which of these we use. And these are going to react to form, it's going to keep deprotonating. It's going to be a full-headed arrow to form H2O liquid and HS minus. So which of these corresponds to that reaction? Reaction C. If we added in an acid, it doesn't matter what strong acid, it would react with the base and we would get H2S. But we didn't do that. We added in a strong base. This question is asking us to relate pKa values of a few different chemical species with what is the strongest base. So there's 2 relationships here that we need to keep in mind. First of all, what does pKa mean? So pKa means the negative log of the acid dissociation constant Ka. So the implication here is that the lower the pKa of an acid, the greater its Ka. So a lower, more negative pKa means a stronger acid. The second thing that we need to keep in mind is we're looking for the strongest base. So since we're given information about the Ka, we need to use the relationship that the Ka of an acid times the Kb of its conjugate base is equal to a constant, Kw, autoionization constant of water. So the implication here is that the weaker the acid, the stronger the conjugate base, and vice versa. So essentially, we're looking for the conjugate base of the weakest acid. Because the weaker the acid, the stronger the conjugate base. All right, so as we look through here, a few of these are just acids. So like hydroiodic acid, HI, we can eliminate that one. Ethanol here, not actually really that good of an acid. It can be deprotonated, but still. Now then, between the remaining 3 choices, I minus is the what of a what, therefore making it what. It's the conjugate base, air quotes, of a strong acid, therefore making it negligible. So then between these 2 other molecules, we have acetate. So acetate, we can see the pKa of acetic acid is 4.74. But if we look at this molecule here, this is acetylene, C2H2. It's got a pKa of 25. This is a very, 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 very weak acid, which makes this choice an incredibly strong base. So the weaker the acid, the stronger the conjugate base. This one being the weakest acid has the strongest conjugate base. In this question, we're trying to figure out which statement is true about a basic solution. So for basic solutions, really for any aqueous solution to be basic, it just means that the hydroxide ion concentration needs to be greater than the hydronium. And for our purposes, hydronium, we can either look at protons H plus or H3O plus. So the answer is C. Now, really, in any aqueous solution, there will be some amount of both hydroxide and hydronium. They both exist in the solution, but they're antagonistic to each other. As one goes up, the other goes down, and vice versa. So for something to be basic, it just means that we need more of the OH minus. All right, in this question, we're looking at ascorbic acid, better known as vitamin C. It's actually a polyprotic weak acid. It's got 2 protons it can lose, hence the H2. And we're trying to find the concentration of the ascorbate anion C6H6O6 2-. Now, there's a really, really cool little rule that we can use here. So technically speaking, we could do 2 ICE tables here. If we think about both of these dissociations, so Ka1 would be the first dissociation. And so the first dissociation would look something like this. H2, and then our ascorbate anion. And it's dissociating into H plus and H, and then our biscorbate anion. So, as it dissociates, what do we know about the relative concentration of H plus and the biscorbate anion? Well, for every one of these, we would get one of these, right? It's a 1-to-1 ratio. So let's keep that in mind and look at the second dissociation, and we'll see a really cool little rule that we can use here. So Ka2 would be the biascorbate anion. Oops, I put a 2-, it's just 1- here. Turning into, and it's giving off an H plus, and turning into the ascorbate anion. So if we look at the equilibrium expression for this last reaction here, Ka2 is equal to the H plus concentration times the C6H6O6 2-, all divided by the HC6H6O6-. Now, remember what we said from before about the relative amount of protons and this ion here. So it's a 1-to-1 ratio, right? Look at Ka2, it's such a small number. 1.6 times 10 to the negative 12, that's so small, that's measly. So that relative concentration of H plus to C6H6O6-, it's not really going to change that profoundly. So it turns out that this and this are going to cancel out, and we get this really cool rule that we can use. And this actually works for any polyprotic weak acid. The concentration of the second conjugate base, I'm just going to say generically A 2-, is going to be equal to Ka2. So really, all we have to do is look at Ka2 and 1.6 times 10 to the negative 12. Great. That's actually our answer. So long story long, the concentration of the second conjugate base is just going to be equal to Ka2. In this question, we're going to go through an adventure. We're going to go through a titration curve. And so let's write out the reactions that are occurring. First of all, so we're starting off with this exciting new acid, nitinianic acid. Cool. So we're starting off with just H2NTO4. Okay, so we're starting with just that. That's what we're going to have at this initial point right here. So H2NTO4. Now, as we start the titration, what's going to occur? So we're going to be adding in hydroxide. And whenever we add in hydroxide, remember hydroxides are going to keep ripping off protons, as many protons as they can. And they're going to form H2O and HNTO4 minus. And let me move that so you can see it a little bit better. So what we're going to have is, we're going to end up going through this buffer zone. And in this buffer zone, we're going to have both H2NTO4 and HNTO4 minus. Okay, so eventually though, something's got to give. And if we have an equal number of moles of OH minus and the H2NTO4, we're going to reach the equivalence point. And at the equivalence point, what's going to happen? Well, we're going to use up both this and this and only be left with water and this first conjugate base. So at the first equivalence point right here, at this point, all we have is HNTO4 minus. Okay? Now, it should be noted that whatever strong base we have, be it like NaOH or KOH or LiOH, we're going to have some sort of cation here counterbalancing these charges. But in this case, we're just told it's a generic strong base. So other than whatever cation that is, all we're going to have is the HNTO4 minus at this point. But then if we continue the titration, this is what happens. So we have our HNTO4 minus. And if we add in more hydroxide, well, they're going to continue to neutralize each other to form H2O, pretty classic. And then I guess this would be the nitinate anion, NTO4 2 minus. So as we add both of these in, we're going to use up this and form this, and that's what we're going to have actually at the point that's we're asked about. So this is going to be a combination of HNTO4 minus and NTO4 2 minus. And if we kept adding in more hydroxide, eventually we would get to the second equivalence point where we would only have NTO4 2 minus. And if we kept adding in more stuff, we would have NTO4 2 minus and also just hydroxide. At this point, just really, really, really basic. So specifically, the point that's labeled with this point in caps, we'd have both of these chemical species. So the answer is, HNTO4 minus and NTO4 2 minus. Okay, in this problem, so we have a patient presenting at the Mount Nittany Medical Center after consuming an unhealthy amount of licorice. So it turns out, and this is true actually, that prolonged licorice consumption, we're talking like bags of licorice every day for a long amount of time, can cause what's called metabolic alkalosis. More on that in a moment. So anyway, they've got all sorts of problems here. And we end up seeing that we have blood concentrations of H2CO3, which is the carbonic acid, and HCO3 minus, which is bicarbonate. Now, how are these two things related to each other? Well, they're a conjugate weak acid, weak base pair, right? Wait a minute. Hark! Weak acid, weak base pair, we're looking at a buffer. We've got a buffer solution, which means we can use Henderson-Hasselbalch to figure out the pH here. And that's precisely what we're going to do. So with a buffer, we can use the Henderson-Hasselbalch equation. pH is equal to pKa plus the log of the concentration of base over acid. And it doesn't have to be concentration. It can be any ratio of conjugate base to conjugate acid. Oftentimes in concentration, but we can use moles, millimoles, millimolar. We can use millimoles per liter, which is also millimolar. Anyway, let's figure this problem out. Now then, the question is, which K do we use, Ka1 or Ka2? So let's consider the two dissociations that we have going on here. Ka1 is going to be our fully protonated acid, H2CO3, dissociating into H+, and bicarbonate, HCO3-. Ka2, on the other hand, is going to be HCO3-, dissociating into H+, and CO3-2-. So which one relates the conjugate acid-base pair that we have? So notice that our acid-base pair is H2CO3 and HCO3-, so that's going to be Ka1 that relates those two. So we can plug everything in. pH is equal to pKa, negative log of Ka1, 4.3 times 10 to the negative 7th, plus the log of, and our base concentration is 38.2 millimolar per liter over 2.2. Let's see what we end up getting. So we end up getting that pH is equal to 6.37. That's the pKa from here, plus, and then it's the log of 38.2 divided by 2.2, which is 1.24. And so this ends up equaling 7.61, choice E. Alrighty, so a person who really likes titrations with both strong acids and strong bases titrates sodium hydroxide with hydrochloric acid. We want to know the resultant pH. So the net ionic equation for any strong acid, strong base titration is just H+ from the acid plus OH- from the base yields H2O liquid. Okay, so there's our neutralization. Now, for any titration, when in doubt, is it out. We're going to do an ICF table. And remember, we need to use moles. Really, really important to use moles here. And to do that, we can use the relationship that moles are equal to molarity times volume in liters. All right, so for both of these, first of all, for the NaOH, it's 0.25 liters from the 250 milliliters times 3 molar, which is equal to 0.75 mole. So we'll plug that in for the hydroxide. Because remember that the sodium is just negligible. It's just the hydroxide that we care about here. And then for the HCl, it's 0.4 liters times 1.5 molar, which is equal to 0.6 mole. All right, so next we identify the limiting reagent. Nice thing about acid-base chemistry, it's a 1-to-1 ratio, so whichever one we have fewer moles of is going to be the limiting reagent. So that's this. This is going to be minus 0.6 minus 0.6 to give us 0 and 0.15. And in all these titrations, we can assume that the change in the amount of water is negligible. So basically, this is a battle of attrition between H+ and OH-, and the winner in this case was hydroxide. So we have a basic solution when it's all said and done. Now, to figure out what the pH is, let's figure out what the pOH is. So the hydroxide ion concentration is 0.15 moles of hydroxide divided by the total volume. And the total volume, we had 250 milliliters plus 400 milliliters, so it's a total of 0.65 liters. That's the sum of those two. And this gives us 0.23 molar hydroxide. Okay, now we know that, we can find the pOH by taking the negative log of the hydroxide ion concentration, a negative log of 0.23, which is equal to 0.64. Cool. Now then, what are we actually looking for in this problem? Are we looking for pH or pOH? Well, we can see that we're looking for pH. Always make sure that you're answering the question that's given. And we're close to it by knowing the pOH, but we need to use the fact that pH plus POH at 25 degrees Celsius equals 14. So we'll subtract this value from 14 and get our answer, which is the pH is equal to 13.36, or choice E. In this question, we're trying to identify buffers. And recall there are two different ways we can make a buffer. First is we can have a conjugate weak acid, weak base pair together in appreciable concentrations. Okay, so that's one way. The other way is through a titration. And there's two different flavors that can give us a buffer. We can either have a weak acid plus a strong base, or a weak base plus a strong acid with an important caveat. And that caveat is we need to have more moles of the weak stuff. Because if we have more moles of the strong stuff, we overwhelm the weak stuff. It breaks the buffer. So we need to have more moles of either the weak acid or the weak base, depending on what type of titration it is. So as we go through these, the first one is acetic acid plus sodium hydroxide. And you can always calculate the moles of both of these. But if we look at these numbers here, it's an equal volume of each of these. But our concentration is greater of the weak acid than it is of the strong base. So this one, we're actually going to give a ding, check mark 2, because we have more moles of the weak acid. And again, you can calculate it. It's 1 mole of the weak acid and 0.5 mole of the conjugate base. Now for the next one, it is a strong acid and a strong base. A titration of a strong acid and a strong base is not going to give us a buffer. It's going to give us either an acidic solution or a basic solution, depending on what you have more moles of. Or if you have an equal number of moles, as is actually the case here, you're going to end up with a neutral solution, but it's not a buffer. All right, so the next one is a solution consisting of this weak acid, CHCuO, aka acetic acid, and CHCuNa. Well, what's CHCuNa? Well, CHCuNa, the Na doesn't matter. That's just a counterbalancing ion. It's just the salt of the conjugate base. Wait, conjugate weak acid, weak base pair. Guess what we're looking at? Dun, 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 dun. It's a buffer. And then finally, in the last one, we have an equal number of moles of the weak acid and the conjugate weak base, and the strong base. So this is a titration of the weak acid plus a strong base. Equal number of moles of both. That's going to break our buffer, so this one is not a buffer solution. So the answer is 1 and 3 only. And in this question, we're looking for which of these is a good Lewis base in aqueous solutions. In terms of Lewis bases for organic molecules, we want to look for amines. Amines are great Lewis bases. And so the only one here that fits that description is this right here. What makes a good Lewis base is it has this lone pair of electrons that it can use to donate. So the answer is A. B, iron 2 plus is a good Lewis acid. C, there are no lone pairs to donate here. Notice that they're all just bonding pairs. Methane, this molecule is very stable. And A plus is a negligible acid. And then H2, the structure of H2 is just this, no lone pairs to donate. So we want something that can donate a lone pair of electrons. It is choice A.